Okay, so to start us off, we'll be hearing from Dijam Panigrahi and Bhaskar Banerjee, co-founders of GridRaster, a cloud-based platform used for social enterprise mixed reality applications. As an introduction, Dijam Panigrahi is the co-founder and COO of GridRaster, where he focused on driving business expansion and marketing strategies. With 20-plus years of experience, he excels in developing and commercializing immersive XR, mobile, and network-based products. Passionate about today's transformative potential, Dijam embraces disruption and finds interest in the fusion of mobile tech, AR, VR, cloud computing, and AI. Prior to GridRaster, he held roles at Texas Instruments, Freescale Semiconductor, and HCL, refining his technical acumen and shaping his business vision. Bhaskar Banerjee is the co-founder and CTO of GridRaster, leading the company's technological vision with expertise in 3D AI and computer vision. He has over 20 years of experience in R&D and product development, having previously contributed to Apple and Broadcom. He holds degrees in electrical engineering from Georgia Tech and has a strong background in academia and industry, which is critically shaping GridRaster's technical trajectory. So now I'll have our speakers come to the stage and get started on telling us about transforming industrial AR with millimeter precision 3D AI.
Thank you, Melissa. Good morning, everyone. Hopefully it's audible. It doesn't get better, right? Friday morning, last day of Expo, so awesome. Yeah, so today I'm Dijam. As Melissa introduced, I'm one of the co-founders and the CEO of GridRaster. I have my colleague Bhaskar, he is the CTO and co-founder of GridRaster. Today we're going to talk about like some of the, we'll pick some of the use cases and talk about how the millimeter precision.
That's the next one. Yeah.
This one.
That's the laser pointer. This is the next one.
Okay. So we're going to talk about some of the use cases and how the millimeter precision AR is enabling, unlocking some of the use cases in automation, robotics, and digital twin use cases. Before we kind of go into the detail, I'll take a little time to kind of introduce just the company and our focus, what we are doing here. So we specialize in kind of bringing in this XR infrastructure that enables you to kind of run, complex experiences and, enabling like experiences that can augment both the human and the machine performance. We have been working with both the Department of Defense and as well as with the commercial industry to kind of build what we have built. Our core technology breakthroughs focuses on just bringing in the cloud to act as a co-processor to all devices that you see. And in the process, we have been able to kind of enhance the performance and get some precision and scalability, which you otherwise will never be able to achieve. Then the precision 3D AI enables you to better understand the spatial environment with the context and be able to guide you through the different processes and be able to enable some of the use cases. If you don't have the precision, you won't be able to do that. And lastly, end of the day, like anything that we do, and what we have seen over the last few years, invariably the POCs and pilots can result in some phenomenal ROIs, but then the enterprises struggle when it comes to scaling those deployments. So we take out that problem as well by having our agile, the cloud-based orchestration deployment, and which allows you to scale seamlessly across different locations, many users. And we are fortunate to have in this time like some of the contracts which are sizable, which kind of allows us to now build for the larger industry. Primarily our focus is on the maintenance and operations. We are solving for some of the challenges in manufacturing and assembly, some of the trainings and simulation use cases, as well as robotics and automation. For this talk, we'll be focusing primarily on the automation, robotics, and the digital twin use cases. And so as I talk about just going a little deeper into the challenges that technically the industry is facing, is one of the key things is the ability to be able to generate the 3D models with low cost and at speed, which will allow it to be then consumed in the various use cases that's been kind of built out. That has been a challenge across the board that we have seen, and we are solving to some of those challenges, and we're going to talk a little more about that. There is also, once you are able to create those models, the need to be able to take that and contextually align that in the physical environment, visualize the components in context with the operation that we are doing. That also has been a big challenge, and we are solving that with our 3D AI component. And also, like particularly if you're the ability that we are now able to digitize the physical world and now taking it to the cloud allows us to kind of simulate a lot of these processes and visualize the challenges which will happen in the physical world. You solve that in the virtual world and then basically implement your insights in the physical world so that you can avoid those challenges that will come. And all this, what we are solving for, has enabled our customers to bring in the performance, which is like they can get any complexity of the models. And in terms of functional fidelity, in terms of visual fidelity, we are able to provide that performance by utilizing our cloud architecture. Bring in the precision, we can align the virtual objects at millimeter precision for our customers now, and scale that. Not only like we are talking about doing like 10 users using a POCs or pilots, but how do you scale that to hundreds of users? How do you scale that to the enterprise grade and multiple locations? So all that complexity is what we are addressing with our architecture that we have. And in the whole thing, one of the key things that has been focused is how do you meet the stringent security requirements, and there are layers that we are building there. And the foundation of what we are doing lies on the architecture that we are pursuing, right? So we essentially treat the devices more like a collection of sensors and the optical display. And more heavy lifting is actually done on the cloud. Or when I talk about the cloud, it could be even an on-prem server, okay? And all the challenges that kind of involve around that, how do you maintain the latency? How do you orchestrate them? Like how do you utilize the wireless, optimize the wireless bandwidths? All of those things we take care as part of the GridRaster architecture we have, it has enabled us is take any of the enterprise applications that are there, be able to deliver into any XR devices by agnostically running that on any of this cloud environment, right? I'll let my colleague talk a little bit about the key ingredients there, and then we'll talk about the use cases.
Thanks, Dijam. Good morning, everyone. So as Dijam pointed out, one of the key aspects here is to decouple the compute capabilities of the devices from what we actually need for high performance, high precision AR experiences for enterprise applications. And to that effect, what we do is we, again, treat the devices essentially as a collection of sensors and displays, and send all the data back and forth from the device to a processor which can actually do this stuff, which can be on-prem server, PC, laptop, depending on use cases, and in some cases just the cloud, government cloud or private cloud. And that allows us to really generate high quality meshes, generate really high quality AR experiences without need to decimate models to make them fit the devices. We don't have to be limited by what the devices can do. And to that effect, what I'll start with is our ongoing work on AR for robotics. And this is interesting because this kind of brings in all the good things about AR and merge it with a real-life application of robotics. One of the key challenges in in robotics, in especially where the robot can actually move freely in a 3D environment, is how do you locate the object on which to go and perform the task, and how do you identify that object so that your task is appropriate for that object. And what we are doing is using the capability of the HoloLens, for example, to identify the object, to register the object against a 3D database of objects that we already have, let's say, and then locate that object in the 3D space. So the agile device localization, registration, and then we track that object, right? So we can then share that information with the robotic system, transfer the mesh model as well as the bounding box of the object, so that the robot can go and perform its task on that object. In addition to sending that information to the robot, our system can actually take the path planning data that comes out of the robot and then visualize. We can align the robotic arm model virtually on top of the robot and then simulate and visualize in 3D what the robotic intent is going to be, what the robot is going to do, right? And fully visualize the entire process, the movement of the robot in 3D space, go and perform whatever task it needs to perform and see the end result. Let's say it's a paint masking process. We can see what is the coverage on that object. Did the robot do what it needs to do? Did it achieve the paint thickness that we need to do? So all those kind of things we can actually now get from the entire AR/VR system. All of that is not completely working yet. It's a little bit of a work in progress. We are in the middle of a 4-year contract with the Air Force, a $5 million contract that we started last year. To that effect, the first step of that is obviously, as I mentioned, to identify an object in space. Can we use the sensors on devices like the HoloLens to capture a high-quality 3D mesh of the environment? And the fact is, yes. The sensors on these devices are actually quite good, right? It's the processing that is limiting. It's the memory that is limiting, right? If we actually can take the data and send it, I don't know, this is the laser? Yeah. If we capture all the frames with the device, the color frames, the depth frames, the IMU sensor data, which is tracking our movement, and send it, the raw data, to the server, we can actually put together a pretty high quality 3D mesh. So here on the right, you can see myself and my colleague Rishi. We are scanning actually an aircraft wing at the hangar at an aircraft depot, Air Force depot, and then sending all the frames to the server and generating this point cloud, right? And then once we have viewed it, we can actually convert it into a high quality mesh. We can actually send it through our AI platform and segment the objects out. We can focus only on the wing while we delete everything else, right? So a lot of that can just be automated with just the HoloLens. You walk around the object, generate this mesh, process it, and you have a high quality 3D point cloud, 3D mesh in minutes. The current workflow requires us to walk around with a 3D scanner, and it's hours worth of work. And then you have to remove it because the robot is going to come and do stuff. Here, the person just wears the HoloLens and walks around. The accuracy is pretty good. As you can see, some numbers here, which compares the actual expected value versus what's their point-to-point distance in the mesh that we create. We are kind of well within the 0.1% threshold here. So a few centimeters, half a centimeter here for a dimension of about 7 meters on the side, right? So that's pretty good for many use cases. Not all use cases, but many use cases. We take this, and the other application we can focus on here is, now that we have a mesh of what it looks like, if we have a ground truth, if we have a CAD model, which is the representation of how it should be, we can actually do a diff pretty quickly. We can, because we are able to align the two objects, we can set a threshold that anywhere you see a difference greater than 1 centimeter, can we highlight that, right? And that allows us to go and do some defect detection, anomaly detection, try and find out where the scan, the mesh as it is different from what is expected. We can detect defects, we can detect if there is any FOD, a foreign object, debris in the environment, right, in my workpiece. And that allows us, again, to do many such use cases. This is on, again, the wing, and similar things can be done on the radome of an aircraft. So again, we are kind of pushing the limits of the sensors at the moment. We can get about 0.5 centimeter, 5 millimeter accuracies here, but that's just the current generation of devices. Devices will get better. And as Dijam mentioned, what we are building is any device, any cloud. We are kind of agnostic to everything here, right? The processes we build, devices get better. We bring this down from 5 millimeters to 0.5 millimeters, right? So all these things kind of come together to, this is an example to show you how we are doing the alignment of an entire aircraft on the model of the aircraft on top of the aircraft. So in this use case, what we have is a C-130 aircraft, which we scan and create a digital twin and train our algorithms to align the plane on top of itself, and then overlay a paint stencil on top of that. The current workflow is you have a whole bunch of overhead projectors which shine the pattern on the plane. We all know how difficult that can be, right? You have to manually move the things, align them. Someone accidentally hits one of the stands, the whole thing is misaligned, someone has to get, it's a nightmare, right? And a bulb goes out. Now you need someone to go up and replace the bulb. One person is working on taping the things up, he's blocking the light that's coming there. It's just not a scalable solution. And this, even if it works well, it'll work only in one location. Anywhere else you want to do, you again have to go and set up the overhead projectors. What we are doing is anyone who wears the HoloLens looks at the plane and it aligns, right? So you basically have the entire plane mapped. You wear the HoloLens, you look through the sensors. The sensors collect the data. We basically estimate the pose of the aircraft, what angle we are looking at, and then we overlay the entire model of the aircraft with the paint stencil on top of that, right? And this is extremely challenging, right? What I showed you, and we have more such demonstrations in our booth, and Dijam will talk more about that. But what we have here is immensely challenging. The end-to-end distance of the aircraft is of the order of 100 feet, right? So a 100-feet object, if you try to manually align, is impossible to do. To be fair, even if it's a 10-feet object, it's very hard to do manual alignment. But here you will see the entire aircraft aligned to itself, right? Automatic alignment, automatic object tracking. It does not matter. We are not using simple things like just the edges of objects, which allows very good alignment for rectangular objects or regular shapes. We use a hybrid technology to do these alignments. We are using both color and 3D frames to estimate depth, to estimate different shapes and features that are there in that object, and use them to align. So for the entire aircraft, our accuracy is a few inches, maybe 1 or 2 inches, going from one end to the other. If we do it over the wing that I showed you a little bit before, it's of the order of a few millimeters. So the accuracy is pretty high, right? And we are, again, able to do this because most of the work is done on the server. The device has reasonable amount of compute, and you need that to be able to correct for any latencies in the round trip so that you're able to correct the pose at the very last minute, very last second. And that's it. I'll hand it off to Dijam to finish the talk, but thank you.
So one thing I wanted to add there, which Bhaskar kind of missed to mention, was the setup that they have here, what you see, costs $2 million. Just think of it, right? Like you can take few HoloLenses and you can basically address the problem and just completely avoid the cost that was put into kind of setting up this whole infrastructure. And one thing, you have to take the aircraft, put it in exactly the same place, the way it has been calibrated. The projectors has been calibrated. Anyway, so this has been pretty huge. Anyway, so we have our more work at our booth. So I would really like to kind of invite you all who can make it, just come and to our booth. There are a few more use cases that we can demonstrate. You can really try out the alignment all yourself, look at our remote rendering capabilities as well, and and talk maybe a little bit about like the security side, which we didn't cover too much here. How are we addressing it, and what kind of ROI numbers or efficiency that we have been able to bring in to some of our customers. No, look forward to see you at the booth, and thank you, and you all have a wonderful expo.
Okay, we have a few minutes for questions. If you'd like to ask a question, please come up to the microphone so that everyone on the live broadcast can hear you.
Thank you very much for the nice talk. I have a quick question. Some of the use cases, for example, if it's aeronautical engineering, typically if you are checking the quality of your work, the precision requirement is much better. I mean, you want your wings to be precise to micrometer. So what is the advantage of having a system which is accurate only to millimeters?
That's an excellent question. The accuracy is basically the limitation of the sensors right now, but it allows a lot of applications right now which we can meet with these kind of accuracy numbers. For example, the robotics work we are doing is for automatic spray paint, for example, right? So in the spray paint use case, the robot head needs to go a few inches from the top of the object, and then the automatic head of the robot sprays the paint and the head moves, right? So the challenge there is to make sure that the robot goes to the correct location in the room, does not collide with anything else, including the object of interest, and then get close enough but not too close, and then spray. Now, in many cases, because of singularities in robots, even though the whole room is covered, it's not really covered, right? So you can go and look at how the robot will cover, say, the paint on the entire object, and you see in the simulation that if we go and place this object here, we actually don't get the 100% coverage we need. So we need to place it at a different location. So we can guide the user on where to place the object to make sure we get the coverage that we need, the paint thickness that we need, things like that. So in that use case, a 5mm accuracy is very, very good, right? And what they needed before was, again, manually go and scan, right? Create the mesh, go and segment everything manually, transfer the file from one folder to the robotic system, and then go and enter manually what is the location of the object that we have placed, right? So instead of typing 22.5 feet from somewhere, I by mistake type 2.25 feet, right? So the human errors that come into the picture. So it takes a lot of time because, again, you're doing the whole thing manually. You're bringing in a large scanner, walking around that, and then you have to remove it because, again, it's a paint booth. You can't leave the scanner in there. So it's a system fraught with lots of possibilities of errors, and it's time consuming. What we are doing is what used to take hours and a lot of manual intervention is now automatic. The person just comes, places the object, is wearing a device like the HoloLens, walks around and just walks off. Mm-hmm. Everything else is handled automatically by the software.
Thank you very much.
Yep.
One more question, and then we'll wrap this up and go to the next one.
Really impressive presentation and capabilities that you guys have. I'm curious as to when you're approaching enterprise customers with the value proposition of GridRaster, with your sort of distributed network compute and leveraging edge compute, are they seeing is the added cost of compute on the edge being offset by the value proposition of unlimited CPU, GPU compute, no longer having to be on device? Or are you sort of presenting, in the case of the painting, the C-130, it normally costs you $2 million, now it only costs you, whatever. What is resonating in getting enterprise customers to sign up for your services?
I'll take that. Let me put it this way. It has not been easy, okay? So we have been at it for last, 5 years, at least on the enterprise side, okay? Obviously, as a technology, like it is running through its evolution, right? And we have seen that like if we take this conversation at the beginning of the journey to any of our enterprise customers, it's very difficult, pill to swallow for them, right? But the enterprises who have gone through cycle of kind of dabbling with AR, VR, and they have the use cases where they've established the ROI, and now they're looking to scale, is where they are now, the challenges begin to unfold, right? Whether it is around, bringing in all complexity of the models, bringing in, enabling that precision, because POCs and all, you can actually hack quite a few things. But now how do you get that for different models, put it a part of that? That's where we are finding a sweet spot. So we are working with many of the top defense primes right now in many of these use cases. But the good thing is DoD at least has been funding those effort to build this, and that has been huge for us. But yeah, and a lot of this, for example, AR for robotics, not that we knew right from the beginning, not at all. We took the capabilities that we had, we went through the end user, okay, can you do this for me? So, of course, we think we can do that. Then we iterated on that, and then we are able to get those basic numbers that we can achieve. And now we are transitioning our system to a production environment. So the whole cycle took us some time, like close to 1.5 years, 2 years, but it's beginning to happen for us.
Fantastic. Thank you.
All right, thank you guys for your questions. If you have more questions, be sure to visit the GridRaster booth later. And now we'll wrap up and get ready for the next stop. So if you can thank Bhaskar and Dijam, and we'll go to the next one.
Yeah, thank you everyone.